Log on, tune in, find out. Another good idea from Cambridge.
The program is by Kroode, who is manager of seismic technology for Shell at Rijksweg, and his co-author is Dirk Smit, who is his boss.
Yeah, thank you, Bill, and thank you, organizers of this meeting, for inviting me. It's really a pleasure to be here at this wonderful institute. Dirk, by the way, is not only my boss, but also the VP of Exploration Technology at Shell and the Chief Scientist of Geophysics. When we were preparing this talk, we thought to present a little bit about the relation between seismic inverse problems and acquisition. And clearly, given what we've heard earlier this afternoon, that was not a very original thought, but I'll hammer it again, and I'll take a slightly different approach. I'll study two seismic inverse problems that are extremely interesting to us, and we'll look at, well, what sort of requirements are really posed by these inverse problems. The question is, very tentatively, of course, do we need full wavefield acquisition? And yeah, for many people in the seismic business, full wavefield acquisition is clear what it means, but let me say here, you've heard that seismic acquisitions are done by some sort of seismic source which moves over the surface of the Earth. So in principle, it's parameterized by an X coordinate and a Y coordinate of the shaft. And you have what we've seen, these very impressive towed streamer arrays, which also consist of two coordinates, a receiver coordinate in the X and the Y direction. And then there's also time, of course. So we would like full wavefield acquisition means that you would record a 5-dimensional object. We typically don't do that at this moment. 4-dimensional or repeated 4-dimensional. So we're typically well sampled in two source coordinates or two receiver coordinates, or maybe in two source coordinates and the receiver coordinates. But the full 5-dimensional wave fields, we still don't have those. And the question is, do we need those to solve the problems that we are interested in? If you look at the seismic processing, what typically happens is that you start with a data set, and you first need to get rid of coherent noise. Yeah, onshore that is ground roll, maybe can be extremely dominant from an energetic point of view, but I will sort of narrow that down to multiple attenuation. I think we know reasonably well what to do with ground roll, and the fold of the surveys that we acquire nowadays onshore are so high that everything that remains will stack out anyway. Multiples not, and yeah.
Perhaps it should be said that ground roll, aka Rayleigh waves.
Oh, okay. Yeah, ground roll. It's actually, so if you do a survey onshore, you vibrate what the energy mostly wants to propagate along the surface, and typically is responsible for 90% of the energy of onshore surveys, or so, the Rayleigh wave, and it contains little information about the deeper targets, as you can imagine. So multiple attenuation, that's an important problem. Then typically why do we do it? Actually, because most of our imaging algorithms are primaries only. So they can, at this moment, they're so naive, despite all the efforts in multiple inverse scattering, and the most robust ones are based on imaging only the waves that have gone down once and up once, essentially, the primaries. And then there's the final imaging steps, and you have heard that reverse time migration is the most advanced member of the family of imaging algorithms that we have. You see on the right-hand side a set of inverse problems that you can associate with those natural steps in the processing sequence. I will talk in particular about multiple attenuation, but I will call it inverting for the primary wave field. So it's an inverse problem, right? Not so much a forward problem. Inverting for the velocity, yes. I will not talk about full waveform inversion. Kroode did that extensively. I've heard other speakers talk about it today. But I'll talk about wave equation reflection tomography. And then, of course, in the final imaging step, the inverse problem that you want to solve is least squares migration. I'll talk a little bit about that tomorrow in another talk. Okay, inverting for the primary wave field. This all starts with a fundamental relation between primaries and multiples. If you're interested, there's a nice paper here that discusses the marine situation. Wout van Borstel did that together with Jacob Fokkema. And it is explained in this cartoon. So if you have a seismic source over here, okay, the energy can go up, down and up once. This would be the primary, but it can also bounce back and then end up in your hydrophone or geophone or whatever. So this is a multiple. If you now, what this relation really tells you is that if you take data originated by a source at xs, and you calculate this integral, so you take the primary data, the ones that have reflected only once, and that you don't know a priori, and you convolve it in time and in space in this manner, so it really means that you sum up over these points x and at the surface of the Earth, then you get a term here that is responsible for the multiples. So what this really says, this equation, data consists of primaries plus multiples. There's one technical detail. These both carry an input signature, the seismic wavelet, and since these terms contain that only once, you have to divide by it. So this wavelet is another unknown in your problem. Typically, you can estimate a little bit, but not very precisely. Okay, this fundamental relation leads to a number of strategies to attenuate the multiples. The most well-known one is called SRME, surface-related multiple elimination, which is a misnomer because the best we can usually do is attenuate the multiples, but so be it. This all goes back to the work of Erik Verschuur in 1991, his PhD thesis, and the first 3D application was actually presented by an old colleague of mine, Jan Biersteker, at the 2001 San Antonio SCG. So what you do, let me switch back to the previous slide. So you don't know these primaries, but what you can do is replace them by data for the moment, and that will, at least for the first order multiple, be sufficient. And thereby, so you make a first estimate of your multiples by convolving data with itself, in essence, right? And then, well, since there is this 1 over W, the wavelet, there's a sort of mysterious procedure that you have to go through, and you have to estimate a filter, a one-dimensional filter, that minimizes the energy in data minus filter times multiples, and then you get the primaries, so to speak. Right? Okay, this is a method that after 2001, after Jan presented this, that this could be done in 3D, has been developed at a very rapid rate by the oil industry, and this is now for long period multiples, read deep water type of application, think about the Gulf of Mexico or so. It is the method of choice. It's very robust. What it cannot do, however, and that's what's not always realized, it cannot handle short period multiples. And the issue is really that short period multiples, so reverberations at shallow layers, you need short period data to predict them. And these short period data are typically not measured because the minimum offset between a source and receiver in a towed streamer type of acquisition is too large, or because there's too much noise close to a vibrator. So the near offset traces are very noisy, and it makes no sense to use those. And the other thing is that this adaptive subtraction mechanism is actually just a trick. It's not based on physics, and therefore it is dangerous. It may actually lead to damaging the information in the primaries. You may accidentally, especially when multiples and primaries overlap, you may subtract something that you didn't want to subtract. Okay, so in an attempt to address these problems, Jan Biersteker, who's been working on multiples for 30 years at Shell, that's quite amazing, so you can build a career on this. He developed a multi-dimensional deconvolution scheme. So what you really So think about the multiples again, but now you have the unknown primaries. You just write them as x, and you're going to estimate x. It's now a multi-dimensional filter. And once you have x, of course, you can estimate the primaries like this. So these multi-dimensional deconvolution methods, they work as well, and they are at the moment the method of choice when you have short period multiples. So for example, shallow water, or in a land setting where there is a shallow hard layer which is causing all sorts of short reverberation. I'll show some examples in a while. Yeah, there is of course a couple of downsides. It again is an adaptive subtraction mechanism, so it is quite easy to subtract too much, and you never really know, is this going in the right direction, yes or no. And there's also of course this artificial divide between long and short period multiples. What is long and what is short? I know that 500 milliseconds is a long period, and I typically would use SRME. I know that 100 milliseconds is short, but there is some sort of gray area in between, and that's typically of course where the hardest problems are, that you don't really know which method is preferred. Okay, recently Erik Verschuur and Gert-Jan van Groenestein came up with a new strategy, again based on this very simple equation. So think about this equation again, as the data is the primaries plus the multiples, and the primaries we're going to replace by x, but well, x is now sort of a sparsified primary, right? So it's only the real primary is a wavelet times that x. So you could think about a seismic wavelet, and then you replace that wavelet by a little spike, and then it can be convolved, of course, with that wavelet. So think about x as a set of spikes, and about w as the actual seismic wavelet. And so what we're now going to estimate is a spiky x and a wavelet at the same time. Seems like a dangerous proposition, but that is what they've done. And the beauty of this formulation is that it handles all multiples, long, short period, all at the same time, all orders at the same time. It's based on very simple physics, namely data is primaries plus multiples. So you should presumably run a smaller risk of subtracting too much, because this is a criterion based on physics, not so much on image processing. And there's a couple of questions here, and those are of course what I'm most interested in. I'd like to show you how this works, and this animation has been courteously provided by Erik Verschuur on a PGS data set. So you start off with data, and what you want to do is you want to separate it in primaries and multiples, and at each iteration of that inverse problem you just calculate the difference between the data and the primaries plus the multiples. That's called the residual. So you start off at 0, so the residual is just the input data. Then you open up a small window in which presumably there are only primaries, and then you estimate the wavelet, you estimate the spiky primary, and then you start to feed the algorithm. So it's important that it's just a it's a steepest descent type of minimization strategy that has been chosen by Erik, and it's important that at each step you truncate the wavelet in time and you sparsify the solution that you get. So it's quite involved, and I'm certainly not saying that this is the final solution. Actually, it's a nice challenge to inverse problems people to come up with better strategies to do this. The point is that Erik and Gert-Jan have come up with a method that may be involved, but seems to generate results. So while you iterate on, you move your window down in time, and gradually you start to explain the data as the sum of primaries and multiples. So you see the residual now is very low frequent, and this actually seems to work. Notice that we took 100 iterations, Each iteration involves evaluations of that cost functional, which is just it has a convolution of data with itself, and therefore it's about one SRME. So if we thought that SRME was expensive, when we started doing this in 2000 or so, you now need 100 times that type of. So we'd be very pleased with a method that can do this a little bit faster. Okay, is this does this work better actually than the classical decon method? That's the next question. So here you see a synthetic. This is an synthetic model, and this is a short period multiple problem. You see the water layer over here in the density model. So this is going to generate a strong train of short period multiple. What we did is we generated finite difference data over this, and then you make the stack, which is, we've heard that very nicely explained what it is. It's the first crude image, actually. If I go back to the actual model, you see all these features here. These are floaters, carbonate floaters in salt. So very high velocity reflectors, 55 and 100 meters per second or so. And you see these things coming back. Here are the floaters. But you also see zillions of repetitions, and that's just caused by that multiple of the water bottom. And maybe other multiples of other layers. It's very clear here what's going on. Okay, so this is our best effort with deconvolution. So I'll flip up and down. This is what we do for a living. Certainly better, but as you can see, this is attenuation, not elimination. Elimination is a misnomer. However, if I go to the EPSI, so estimating primaries of sparse inversion, by sparse inversion, then you see that it takes out yet a lot more. Okay. So yes, we do believe that it's better than deconvolution. Another way of judging the quality of this result is just by looking at the image. So we ran these through reverse time migration and just image the data. And in the back you now have the impedance model. It's a synthetic example, so it's very clear. And this is the raw input data before the multiple that we image. And then the same, but now for the EPSI data. Right, so I'll flip up and down. And you can all see that this is really doing something that it should do. Another part of the section, that's the nice thing about synthetic model. There is no reflectivity below a certain, if you just stop building the model over here, then there shouldn't be anything here, right? That's a telltale. But this is what it does. So, yeah, very pleased. But then, of course, this is synthetic and the world isn't synthetic. So, let's move on to real data examples. This is the Middle East. And what you typically see is that the geology in the Middle East is not very spectacular. It's layer after layer after layer. However, the multiple problem is really, really formidable because of all these layers. So many of these layers that there's typically in evaporite that you see all over the Middle East. It's called the Rus. It's at 100 meters depth. You don't even see it here because it's so shallow. And it's generating tons of multiples. And all the other layers here, multiples. And so after you have removed 90% of the ground roll, that's 90% of the energy in the data, there's 9% left in multiple energy and maybe 1% in primary energy. That's the game that we're playing on shore. So, okay, I'm going to toggle up and down, and because, well, if you don't have an experienced eye, this is difficult. I have pointed a couple of arrows, so just focus at one set of arrows or so, and then you'll see what happens. In the yellow box, you see that the continuity of that reflector is increasing a lot. There's also an ellipse, and you see here a little feature here, right? It's just a small feature that was just obscured by a multiple, presumably, or.
Sorry, how do you know it's real? When this is real data, how do you know the feature's real?
Well, to be honest, we don't. It's only if you if you drill a well, we will know. But I'll tell you that some of these features, there are plays that depend on these small features. So at this moment, it's only mathematics that we apply on real data.
That V shape you're saying it's real?
I think it is. Yeah.
Because it looks artificial.
Well, you have to take into account that this has not been really imaged. This is just a stack, which is really a crude image. Right? So we should run a reverse time migration or so it will properly image.
Quick comment on this domain interpretation. I don't know what that particular feature is, but often in the Middle East you have these successions where you have carbonates, and some of the carbonates have thick faults in them, which are just in the carbonates, and they'll show up like that. And we're after those carbonates. That doesn't mean that that's what it is.
So what you're saying really is, based on experience, that people look at these and then sometimes they do drill a hole and see what's there.
Oh yeah.
And
Well, this is the
so
most prolific hydrocarbon compounds, right, in the world. So we do drill lots of holes here. So we know a bit, but I don't know about this particular. Here's another one. Oh, I think it's obvious, right? So it seems to work. It seems to work. Amazing. The real question is, can we now, so we are where we are with SRME, the standard long period surface multiple elimination in 2000. Can we generate this to 3D? Well, yes, I mean, the code is there. So this is the BP synthetic that you saw a number of times today, which we extended in an invariant fashion in the cross-line direction. So then it's easy to generate a 3D survey because just one line is enough, and then you translate that, and then so this is just an image. It's an RTM image of the data, of all the data without multiple attenuation, and here you see the one where first of all we've done a 2D inline type of EPSI. That should be enough in this laterally invariant medium, and then the other is a full 3D attenuation by summing up over all 3D data that we had here, and yeah, synthetically you can play these games, of course. Okay, now comes the key question: what sort of requirements does this pose, this formulation on acquisition? So here's the formula again. I've explained to you that. Let's see what we need to do. We need to evaluate this integral. So for a given shot coordinate, we need to sum up over axes, two axes, x and y, right? And since the right-hand side is a shot coordinate, this x will stand for a receiver coordinate, which means that you have to have receivers everywhere, essentially, in the x and the y direction. So each shot has to have receivers everywhere. Now we have data sets like that. That's okay. So what will it mean for the axis? Well, this has to be everywhere, and the receivers have to be everywhere. So the axes have to be 5-dimensional objects. So there are many more axes than there are data. That is the real problem. I mean, I can evaluate that integral. X is, after all, unknown, so I can start with zeros and then hope that it will iteratively go to where it should go. But I have to take into account that there's so many more unknowns than knowns and data. I've sort of looked at the best sampled surveys that we acquire at the moment. In the Middle East, we shoot at 25 by 25 meter grids, and we have 100 meter line spacing. Those are the best. And you would like to invert X on a 25 by 25 by 25 by 25 meter grid. So there's 4 times more unknowns than data. That's the fundamental problem. In the Gulf of Mexico, it's slightly worse. For the Toad Stream WAS surveys, I think that there's 5 to 10 times more unknowns than data. Okay, so what should we do? What can we learn from 3D SRME? That's after all, we had similar problems there. Can we learn? Can we do interpolation on the fly, or what's the Can you benefit maybe from another formulation of the problem? This is proposed by Delft again. You replace the x by a linear operator on an extended image or so, and that this would then be yet another inverse problem, which you could call imaging with multiples. Possible? Oh no. You can also try to solve this, at least for open terrain, think desert type of acquisition, in acquisition, to go for acquisition of the full wavefield. Done some cost calculations. We have a supercrew running in Oman. It's about a small village moving in the desert there. It's 500 people. They have 25,000 channels of 12 geophones each, so 300,000 sensors on the ground, and they move 24,000 per day, and the productivity is about 25,000 shots a day or so, using this distance-separated simultaneous shooting. Line spacing, yeah, the best line spacing is 100 meters, but more default is 200 meters. And you can calculate the cost of acquiring the seismic per square kilometer as a function of that cross-line spacing. You really wanted to move to 25 meters in order to have a full wavefield, right? So that doesn't look too good for two reasons. It goes up, of course, and also the channel count goes up rather dramatically. You can do a little bit better if the hardware were extremely inexpensive. This is so if the hardware were only half the price. There is obviously a depreciation component in this story. So if the hardware were half the price, then the curves get more flat. But still, you need many channels. This is a nice graph that I picked up from my first break publication by Bob Heath. It's just channel count as a function of time. There's a Moore's law for channel count onshore. It doubles every 4.5 years or so. It's slowish, but it's still exponential. And Bob is a very optimistic person, as you see by his interpolation of these data points. So it's he arrives at somewhere around 2020 for the 1 million channel mark. It's probably more like 2025 or so. That's a bit too late. I'm not sure that I will still be working by that time. But what we have set out to do actually is try to come on a different trend curve. So we would like to be there 10 years sooner. And the initiatives that we're undertaking are featuring here. So we've set up a project with Hewlett-Packard to arrive at extremely low cost, lightweight, low power type of wireless acquisition. Seems obvious, but and it has been referred to by Dave as well in his presentation. That's the way to go. Another project that we have is working with PGS on fiber optic acquisition technology. The great thing about fiber optic is that, yeah, the cables are extremely inexpensive. It's just a standard telecom cable that cable companies put in the ground for your internet subscription, right? So it's 50 cents a meter or so. It's you don't need power along the line because it's just laser light that go through the line. So you only have power here at the beginning of the line. At the beginning of the line, there's a cabinet of these lasers that send the laser light in, and it comes back. And then there's optoelectronics converting those light signals again to electrical signals. So that system is actually a prototype. We have tested and it's working well. So we're optimistic that this will actually work. Yeah. I have 15 minutes left and there is a second topic to talk about, namely inverting for velocity. And I was going to talk not about full waveform inversion, but about seismic reflection tomography. There is a construction that is important if you want to arrive at a wave equation-based reflection tomography, namely the construction of subsurface angle gathers. I'll talk about that a little bit more in detail tomorrow, but actually we've seen quite a few of the formulas in Ivan's talk, for example, and I think in a number of other talks as well. So first of all, you take data and you produce subsurface offset gathers. If you do this for h equals 0, then this would be a standard adjoint of the Born equation, if you wish, or which has a nice reverse time implementation. You can shift that, so you don't correlate at h equals 0, but at a finite value of h, and you get these gathers. So what's the point? You can do a slant stack in these gathers, and I'll explain the details a little bit more tomorrow. So you go to the subsurface wave number gathers, and then finally evaluate that for k equals tangent theta, and then you get, according to Sava and Fomel, these wave equation based angle gathers. And tomorrow I'll explain that these are actually the angle dependent reflection coefficients. Okay, here's a couple of examples. This is again the 6P model. You've seen that tip of the salt in almost every presentation today. It seems to be generic. We make these angle gathers at this location. So these are the subsurface offset gathers, first formula. And then you do the Vedon transform and you evaluate at k equals tangent theta, and then you see these angle gathers. It looks really nice. The point is that if the velocity is wrong, in this case too high, this is what you're going to see. So it looks very much like classical reflection tomography. Something curves, it says. But we also say something has move out, and you need to get rid of that residual move out. You need to flatten it. That's basically the principle behind wave equation reflection tomography. So you can do this in two different fashions, and the one fashion is actually goes back to Bill's original ideas in, must be early 90s or so. It's called differential semblance optimization. I've written down the formulas. What I'm going to talk about is a non-automatic version of this. So what we're going to do is we're going to linearize this problem, and we're going to pick the move out, which is very standard in tomography methods. So you pick something and you make sure that the model explains the travel times that you see. So what are we picking? Well, if you think about these image gathers, so you saw in a too high velocity model move out on the curves. In the exact model, it would look more like this. Right? So this is what we would want to see, this is what we see. So this difference you can call delta z of theta, and the index I stands for a particular reflector, or a particular xy location, or whatever, a peak, so to speak. Right? What we can do, and that's really not hard, we can derive a relation between that move out as a function of theta and the perturbation of a velocity in the overburden. I'm going to show you these kernels, these k of x and theta, in a minute. They are really very instructive. In any case, so I would like to minimize, of course, this. I want this to go to 0. I want all these arrows to go to this location. Unfortunately, I don't know this reference, because that's only achievable for the true velocity model. So what we really do is we subtract adjacent thetas, which both have the same reference level, and then you arrive at this minimization problem. So it's a linear minimization problem nowadays. Right? So you minimize for a delta c that occurs in this formula for this particular quantity that you had picked. Okay, I'm going to show you these wave equation kernels that relate move out in the angle gathers to perturbations in the velocity model. It's again the 6P model. So you take an image location x and you calculate these kernels. For a particular theta, this theta is 45 degrees, and it looks very much like a set of specular rays, but they now not rays anymore, they're wave equation objects, because that kernel was just calculated using Green's functions and what have you. Here's one under the salt. And you see that the salt really has an effect on these extended rays, these wave paths. Here's one more. You have to realize if you do standard ray-based tomography, and you would shoot a bundle of rays from this image location to the surface, the rays, once they hit the salt, typically go berserk. They go everywhere, essentially. The salt is too rough, the velocity contrast is too high. This is actually beyond the realm of validity of normal ray-based approximations of the wave equation. But since these kernels are calculated by solving the wave equation, we couldn't care less, right? Wavefronts tend to heal after they hit a highly rugose object. Okay, so how does it work now? So we intentionally used a too fast velocity model under the salt. And then you generate these angle gathers, and this is what they look like. And now we're going to pick the move out, and we're going to basically solve that inverse problem. And so in one iteration, this is what it does. So from here to there, it's flattening as it should. Okay, it was only a linearization of the problem, so we can do it again, of course. And that's what we do, and again. And now there's really no RMO left. However, the velocity model has been accelerated a lot, and as a result, a lot more interpretable primaries came into the image. So you can pick again on the full volume. There's many more now, and you can iterate 4 times more. This is what it is. It doesn't go any further. If you look at the final result and compare it against the true model, this is what you get. It's not perfect, but it is certainly not bad either. This is, I believe, especially since it's somewhat questionable that full waveform inversion would get you below the salt, although maybe in Laplace domain, who knows. This is what we believe is one of the few tools available to build velocity models under the salt. Okay, I want to, in the last 5 minutes, talk about an application of this method, a potential application of this method on the latest and greatest in deep water type of seismology. It's called ocean bottom seismometers. Actually, in the BP talk, that was actually mentioned already. BP was the first company that tried it at Atlantis. It's basically putting these ocean bottom seismometers, these big bulky things, on the ocean floor underneath 1,000 meters of water or so. See, it's quite a bulky operation, and you have these cranes that put the remotely operated vehicles in the water, and you see such a vehicle manipulating such a thing. The idea is that these nodes stay on the ocean floor for maybe a month or so, while a boat, just a gunboat, is sailing over it and is shooting at a 50 by 50 meter grid. So you get axon sampling in the shots in 2 coordinates. In the receiver spacing, you cannot afford at this moment 50 by 50 meters. So we do 400 by 400. That's for purely logistical and economic reasons that we don't go finer. This is a wonderful story for people working for Shell and BP, by the way, who is a partner in this particular one. We had drilled a well based on seismic of the day, which turned out to be dry. That's never nice, but these things happen. And we got the new data, and based on those data, these OBS data, the model could be refined. The image was far better because the illumination on these OBS surveys is far better in general. And it basically could understand why this well was dry. It's basically at the edge of a faulted zone, and probably you shouldn't have drilled it there if you had had that data. So it was decided to re-drill, and we made a big discovery over there, just a few hundred meters away, which is also very illustrative of, how small the difference between failure and success can be, and that better acquisition makes this difference. It's not inexpensive, certainly not if you try this for the first time. Okay, so what I'm going to talk about is that method that I described, wave equation reflection tomography, on this type of data. So we like this type of data, we're making discoveries on it, so we would like to use that much more frequently. But can we do model building based on these type of data with such a coarse grid at 400 by 400 meter? Okay. So we did the same exercise now with an OBS type of geometry, 400 meter node space, and this is 2D, and we generated the gathers in a 2-fast velocity model, and it's sort of clear that, well, away from the salt, which you see the top of the salt, the base of the salt, away from the salt, the events are somewhat interpretable, so you can pick them. This method will work there. Under the salt, it looks very questionable. If you now go to 50 meters, and this is what you see. This is lovely. I mean, anybody can invert, I guess, based on this. Let me zoom in. What you see, the big prominent reflector is base salt here. I'm looking at the 400 meter angle gathers, and this is just terrible. Imagine DSO trying to do this automatically. That's a recipe for disaster, of course. If you had 50 meter node data, this is what you would see. You would see the move out, and yeah, okay, based on this you can try to update the model. Okay, so what to do? This is maybe again a challenge to the inverse problems community. I think that above and in between salt we're sort of fine. You can pick the events there, and so that will likely drive the inversion in the proper manner. Under the salt, and that's precisely, of course, where we want to drill, the gathers seem to break down. People that look at this, especially acquisition people, say, yeah, but of course we didn't design this for 2D purposes or 3D purposes. It's not a 400 meter grid in one direction, it's a 400 by 400 meter grid, so you have quite a bit of fold here. If you think about each node has about 100,000 shots firing into it or so on a 50 by 50 meter grid, so it's more or less a what we call in Seismic a minimal data set. Each node should be sufficient for a very accurate seismic image, leaving alone multivaluedness issues and what have you. So, and you have 800 of those, right? So why can't you? Okay, I don't know. It's certainly true that in 3D this problem will likely be posed better, because what you typically can do, if so this pi here represents all the azimuths that of course aren't present in 2D, but they will be present in 3D, and you can sort of do sub-stacks over the azimuth direction, thereby enhancing the signal to noise and hoping that you will be ending up with pickable events. There is still the option to just solve it in an acquisition, but how? Well, what we're doing here, we're working with a company here in the UK that's developing these James Bond-like devices. I'm always amazed if I see them, but they actually exist. So they're called, well, we call them flying nodes. There are autonomously operated unmanned vehicles or whatever. There's some nice abbreviation for it. And the notion is that they would sit on the backpack of a ship by the thousands or so and would be launched very quickly and would propel to that location and there deliver the OBS sensor, that big bulky thing that you saw. And yeah, if you can do that very cost effectively, you can think about, in principle, about shrinking the distance between the nodes. You can also think about rolling the spread and thereby making it almost like a land seismic survey. Of course, the comment within Shell is, yeah, okay, OBS is just land with a lot of water on top of it. Okay. So that brings me to the conclusions. I think that what I've talked about is multiple attenuation and wave equation reflection tomography. They are among the most challenging seismic inverse problems. They're large, very compute intensive, and need lots of data. The question is very much, what can we do with the current generation data that we acquire? both for the multiples and for the OBS type of data sets. And I've also, well, just given you a sneak preview of these million channel projects and these flying nodes projects that aim to make 5-dimensional acquisition more affordable than it is at the moment. Thank you.
Thank you very much. Perhaps we could take a couple of questions.
I have a couple of questions. Well, my first question is about APE.
Yeah.
I really like how Jeremy's work, so this is not criticism in any way. But the model behind it, this model of sparsity, it comes from the way we think about models. Right?
Yeah.
So it works in syntactics very well because the model is sparse. There are layers in the model. But we know for a fact that the way we look at an outcrop is not the way seismic waves actually see the Earth.
Yep.
So when we impose sparsity to separate parts of the wavefield, are you guys concerned in any way that that can be a problem?
Sure. And by all means, we could formulate or try to formulate the inverse problem in a different fashion, not in employing sparsity or something. I think we would love to see a different strategy to minimize that cost function. But I mean, looking at the real data examples, that's a very impressive stack of reflectors in the Middle East, of course, and it seems to work a bit. I mean, I won't say it's
threw away. That's
sorry.
You don't know what you threw away.
No, that's true. And we really need interpreters to give us feedback, of course. Okay, well, it's like I said, these multiple problems in the Middle East are so tough that we're glad to see progress at all. But you're right.
Another question I haven't asked.
Perhaps we can move on to the final phase of this program, which was designed partly to handle more questions. I'd like to ask the 4 speakers to come up who've agreed to